Okay, good evening, everybody. It's great to see so many of you come back for Donna Strickland's second Einstein lecture. I like to welcome you all on behalf of the Faculty of Science and the Albert Einstein Center for Fundamental Physics here at Bern University, but also in the name of the Einstein Society, which is a co-organizer of this event already since the year 2009. And as I said yesterday, Donna Strickland is our 16th Einstein lecturer in the 6th round that will go from physics today to mathematics and then to philosophy, which has been going on already for quite some time. Today, I would like to especially welcome Virginia Richter, the rector of our university, and I was ready to welcome the ambassador of Canada in Switzerland, but he comes only for the dinner, maybe. I don't know, this I didn't know, but at least he invited Donna and Doug, her husband, and myself for lunch today. But I don't see him here. If he's hiding somewhere, then please feel welcome. And 5 minutes ago, I got an email that the Indian ambassador, Midral Kumar, will also come with his daughter. And I reserved 2 places, but I don't know whether he and she are somewhere. In any case, so you're all very welcome to this other round of Einstein lectures. And as I said yesterday, Donna Strickland is from the University of Waterloo in Canada and got a bachelor degree in physics engineering from McMaster University and then got her PhD from Rochester University, where she worked on ultra-cold, ultra-short high-intense laser pulses, and this turned out to have a lot of implications, first of all in fundamental science, but also in medical applications, which is what we'll learn about today. And also she is very active in climate monitoring, which will be the subject of her lecture of tomorrow, which will be only at 7:30, but in the same room tomorrow. The work is of so great importance that for that PhD work, which she did in 1985, she got the PhD in 1989, for that same work, she was awarded the Nobel Prize. And she is actually, was the 3rd woman to receive the Nobel Prize after Marie Curie had won the Nobel Prize in 1903. And then it took 60 more years before Maria Goeppert-Mayer got the prize, and another 55 years before finally Donna was honored for this wonderful discovery that she made during her PhD. So she shared the Nobel Prize with Gérard Mourou and with Arthur Ashkin in the year 2018. Especially since I expected the Canadian ambassador to be here, and since you told me yesterday that you would be wearing that pin, I am prepared to say something. Donna is not only a Nobel laureate, she is also a commander of the Order of Canada, which is the highest honor that can be bestowed on a civilian Canadian. And so if you look very closely, and maybe if Herr Sorgen zooms in on that pin, we can all appreciate that you have this other very high honor of a totally different kind. I also want to mention that Paul Burkhardt, the vice president of the Einstein Society, showed Donna and Doug the Einstein House, and I was wondering what you may have learned about Albert Einstein. Perhaps you learned that he started in Bern in 1902 as a 3rd-class patent clerk. and only several years later was promoted to a second-class patent clerk. Now this Order of Canada also comes in 3 classes, but I can assure you that Donna got the first class from day one. So I look forward very much to listen to your second lecture, Donna.
Thank you very much. All right, well, let's see how this goes. It might be some false advertising, because you might think I'm going to talk about medical stuff, but obviously I'm a laser jock and really don't know that much. So it's really about the light for the medical application. And it is, my part is going to be with fiber lasers, but I will talk about the biggest lasers as well, but my own part is the fiber. So why do we want to use lasers to accelerate charged particles? Now, we're here in Switzerland, so I'm sure everybody in the room knows that the biggest particle accelerator is here in Switzerland, and it's CERN. And you can see that it is quite large. And it takes 27 kilometers to reach tera electron volts, that's 10 to the 12, or a million times a million. And this is because it uses what we're going to call traditional accelerating, and I'm not going to go into the details because it's not lasers. But it still uses a material way of making the force. And so you can charge one plate positively, you charge the other plate negatively, and then a charge in between, if it's a positive charge, wants to go away from this plate and go towards this plate. And that's the force, and that's what accelerates. And you can turn this up and up and up, but at some point, there will be material breakdown, and you'd basically have lightning from the one plate to the other. And so that's what stops it. So that's the limit, and so you can get about GeV, a billion EV per kilometer, all right? And so if they want to go even bigger, and I'm sure they do, because scientists want to keep on pushing the frontier, it will be an even bigger ring. So back in 1979, Toshi Tajima, along with his colleague John Dawson, theoretically came up with a scheme that would use lasers to accelerate electrons. Right? And they went through their theory, and then they used this example, that if they just had a laser pulse that had an intensity of 10 to the 18 watts per square centimeter, which did not exist at the time, but they're theorists, so they don't have to worry about that. But it was possible. It was possible because at this point, the biggest fusion laser that was in California, they didn't want to focus tight. Had they thought there's a reason, they could have focused that one tight enough to make 10 to the 18 watts per square centimeter. So they said, okay, if with this type of laser, 10 to the 18 watts per square centimeter, we can accelerate electrons to GeV in just 1 centimeter. So it's 100 times shorter distance than this. So this is the promise. And of course, I'll show you we're now at 10 to the 23 watts per square centimeter. Now, there's many things, obviously, CERN doesn't have to worry yet, that go into this. And one of the things, if we really are trying to make light intense, and like I said, that fusion laser could have been made intense if it had focused tighter. But if you focus tight, it leaves the focus very quickly. So you maybe in 1 centimeter could accelerate electrons if you could keep the 10 to the 18 for the whole centimeter, all right? I will tell you that at this point we have hit 8 GeV, so his idea was correct, and so I'm going to go on about it. But I'm not going to really talk about trying to beat CERN. I'm going to talk about the fact that most particle accelerators, I think, are used for medical applications, right? Many people now get radiation treatment, and that's from a particle accelerator at a hospital. And so then the goal really is, can we maybe beat hospital accelerators? And so that's the goal right now. Eventually, we'll want to beat CERN too, but okay. Let's just start with this one. So I'm not going to talk about proton acceleration. I'm only going to talk about electron acceleration because the scheme that I'm going to talk about that Toshi came up with along with John Dawson is for electrons. But the one type of radiation you could have at a hospital is proton acceleration. And as I understand it, again, not a radiation physicist, but the advantage of using protons is the fact that it goes through the body. This is just depth of soft tissue, depending on how energetic it is. So if you really wanted to go 10 centimeters, you do need 120 MeV. But what the advantage is that it doesn't dump its energy, and then all of a sudden it does. Which means if your tumor was 3 centimeters inside, you would tune to have 60 MeV. The energy would dump there and affect the tumor, and not affect all of your healthy tissue on its way to getting to the tumor. And so this is the advantage of using this type of radiation treatment. It really does dump exactly where you want it to dump, okay? As far as I understand, the particle acceleration in the hospitals are more in this range. We can't quite get here to the 10 centimeters. I will tell you, and I'll show you actually, that although these high-intensity lasers started in the United States, Europe and Asia took over. And when I asked the Europeans, and particularly the Germans, how come they could convince their government to build these big lasers, this was the reason they gave. They said, we have said that we're going to try to beat hospital acceleration, and in particular for proton acceleration, to go deeper into the brain in order to get to inoperable tumors inside the brain. So that's the goal for the big lasers, and a lot of research is going on right now towards that goal. Now, on the other hand, the most common type of radiation treatment that you will get at a hospital, as I understand it, is this electron radiation. You'll see that you can go further for less energy, so that's good. The disadvantage of this type of radiation treatment, though, is that you'll see that you're going to start here and radiate, and the energy is dumped until it's gone and it's over, okay? And so if you do want to go 5 centimeters in, you've radiated the whole way in that, and so your healthy tissue is also getting radiated while the tumor is getting radiated. All right, now there's ways around some of that, but again, I'm not here to talk about radiation physics. So, but this is the disadvantage. Now, how did I get involved with this research? Well, Toshi called me up sometime during COVID, I think, and said, I hear you're working on intense fiber lasers, and I have a new idea, and I want you to be part of this project. And so his idea comes from the fact that right now, quite often, cancer patients get all three. They get the chemo, the radiation, and the surgery. But there's some surgeries, like esophageal cancer, esophagus, or stomach cancer, that they can go through with an endoscope, and they can cut it out through this type of surgery. But the surgeon has to decide, in order to make sure I get it all, do I risk cutting too deep? And that has some dire consequences if it goes wrong. Or do I not cut so deep and end up leaving some of the tumor there? And then if you do that, it goes back so fast, why go through the surgery? So Toshi contacted me, he said, I think there has to be a better way. And this is what I would like to see if we can develop. Can we go down the endoscope after the surgeon cuts away the tumor? He or she should leave about a micron thickness of it. That way, he knows he's not cut too deep, he's only cutting out the tumor and not healthy tissue. And he leaves that last micron of it. And then we're going to have our accelerator right in front of the tumor, and it just has to go in 1 micron. That way, it's not going through any other tissue because it's gone right to the tumor. It only has to go the 1 micron thickness of the tumor, and then it can be gone. Now, if you look at that, these are centimeters here, okay? And so a millimeter would be way down here, and microns quite a bit smaller. So you're not talking MeV electrons even. You're only talking 1 to 10 kiloelectron volts. So he said, Donna, for that, we only need 10 to the 14 watts per square centimeter. Can your fiber laser do that? I said, easy. And then I got off the phone and went, oh, yeah, that's right. The gratings aren't at the end of the fiber. Small point, but we'll get to that at the end of the talk. So now that's why we're doing it. So now I'm going to tell you how it works. So this is how it works. And so a lot of this talk is how is a laser pulse like a mother duck. So I'm sure, because ducks seem to be ducks and pigeons are everywhere in the world. I travel the world. You always see ducks and pigeons. So this mother duck is got all of her babies behind her. And maybe some of you are like me. When you see this, you think, how does this mother have such control over her babies when my babies just want to run around like crazy? So maybe she has great psychological control, but no, that's not what it is. So I'm going to tell you what it is. But first, this picture is so great because the rest of the water is so calm. You really see this wake that she leaves behind her, okay? So it's all about the wake, and the mother duck makes the wake. Now, somebody was watching a duck like this on the water, I guess, because this paper just came out in 2021. It's not a really old paper. Obviously, a fluid mechanics person watching this duck, thinking it can't just be psychological control. And so they studied it. And sure, ducks knew this before people, that if the ducks just line themselves up in these wells of the wake, that's where the maximum force they feel, and they get to be pushed along by the mother, by this wake behind her. And so this is what we're going to do. The laser pulse is going to make a wake, and we're going to push the electrons along just like this, okay? So that's the goal. Do we need to know anything else? I don't think so. But we'll come back to this. How is a laser pulse like a duck? But first, the other thing is that we have to understand what this pushing does and how does this pushing lead to the acceleration. And I sort of touched on this yesterday's talk, right? You get the most change in your kinetic energy or your speed if you ski down a really big hill. So this is also true if the hill is made of water. And so I will point out a few things here. The biggest wave you can have, and this is true in water, it's true of an optical wave, it's true of what I'm going to talk about, a plasma wave. The maximum height you can get is limited by this idea of wave breaking, okay? And that's when the speed at the top of the wave is faster than the bottom, and that's what causes it to wake. But I suppose the really good surfers love the challenge of possibly drowning under this wake. So, but the fun is the fact that you can ride all the way down, all right? And the higher it is, the further you have in order to pick up this speed. So now, unlike yesterday's lecture, I'm going to show you the vectors here. And this is something that if you took physics class somewhere, you'll have seen these vectors. Not these ones necessarily, but the one we all know mostly is gravity, and it pulls us down or towards the center of the Earth. I could have called this the normal force, but in water it's quite often called buoyancy. And then, of course, you are being pushed by this moving wave, and so that gets all lumped into hydrodynamic forces. And so you have these three forces working on this person here. Okay. And if you add the vectors, and that means the vectors point in the direction of the force, and the relative length of the arrow gives you the relative magnitude of the force. And so what you see is that the force is not at all, there's nothing perpendicular to this that would go into the water, because this person is not sinking into the water. He's accelerating down the slope and picking up speed as he goes, okay? So this is the first thing, is that why does this type only work with electrons and not with protons? Lasers are being used for proton acceleration, but it's not this type. And the reason is that, again, if you've ever watched surfers, you will see that they swim out to catch the wave, and then when they see the wave coming at them, they'll turn around and they'll start paddling, okay? And they have to start paddling because they have to be somewhat close to the speed of the wave so that when the wave lifts them up, it doesn't just go past them, okay? They have to be ready to catch this wave, start going down quickly, and get to be the speed of the wave, and then they can go faster if they want or go sideways and just go with the speed of the wave. But they must be able to do that. And so what we're talking about, I guess I didn't mention it, at the beginning, I did not give you speeds. When I said we were accelerating the particles, it was always in energy, okay? Because again, the speed and the kinetic energy is related to, the kinetic energy is 1/2 mass times the speed squared. A proton is 1,000 times more massive than an electron. And the light pulse, unlike the duck, is going to move at the speed of light. Which, because I have to mention Einstein every time, I'm going to mention Einstein here. That was his thing, okay? Relativity, the speed of light is the speed of light. So the speed of light in material is a little bit slower, but it's not too slow, okay? And so for electrons, there are schemes that they can get the electrons going so they can pick up and get towards this relativistic speed. Whereas if you were going to use this, the proton would have to have some way of swimming first. And so you would already have to use an accelerator to get the proton up to a certain speed so that they could continue to catch the wave. Okay, so the wave is moving at a speed. The energy is 1/2 mv squared. Okay, and we are eventually trying to get the v up to relativistic speed, which means this is also why, I should be honest here, why it's always talked about in energy and not in speed. Because as you approach the relativistic speed, you can't go past that speed of light, and so the energy starts going into the mass. Right? You quit being the rest mass of the object, and the energy starts going more and more into the mass. All right, so that's why we talk about energies. This is what we want. If you really want, and so what Toshi first talked about, needing 10 to the 18, and now people are using 10 to the 20, is to try to get a great big wave up to the maximum where it's going to break on them. Okay? Right. All right, I showed this yesterday too, and I've already talked a little bit about it, but this is going to be important to understand, is that a lot of physics, again, I said yesterday, is just changing from one type of energy to another type of energy. And so when you take your ski lift up to the hill, it's doing the work against the gravity. When you're at the top of the hill, you have this potential energy stored up, and anytime you feel like it, you can take it back and make it kinetic energy as you go down the hill. Okay? And so the important part is the potential energy can turn into kinetic energy. This time I'm going to talk about how the kinetic energy can also turn into potential energy, okay, when we get there, and that's the important piece of how this whole thing works. Okay, so what kind of wave will push the electrons? So for the person skiing down the hill, for the person surfing on a wave, or you can be water skiing behind a boat on the wake and accelerate down the wake, you are talking about using the gravitational force to do it. It is a material wave, so there's a height change, and then it's gravity. Now, there are 4 fundamental forces in nature: the electromagnetic force, which I'm going to talk about, the nuclear strong and weak force, although you might wonder why it's called a weak force when you consider gravity. Because gravity is the one that should be called the weak force. It's the one we know, and we think walking up a mountain is hard to do. But I'm telling you, it's 30 orders of magnitude weaker than the weak force. So how is gravity not being called the weak force? I don't understand it. So this is why we don't start moving at relativistic speeds. Well, we're massive. But we're trying to get our charged particles up to relativistic speeds. So we need some force. So it's not going to be gravity. So we're not going to surf the electrons on an actual material wave. On the other hand, as I said yesterday, because gravity is the one that we sense, we still always talk about energy in terms of height. So I'll still draw the wave as a height, but it's not a height. It's just a maximum. All right, so what kind of wave is going to push our electrons? Oh, I think I said that. I forgot that I wrote it down. Did I say? I think I said all of that. Yep. Okay, so I also showed this one yesterday. This is the pith ball. And so Coulomb showed us that there is a static electric field between charges. And so the one charge feels the force because of another charge. All right? But we sort of, in physics, want to think about, why does this charge feel the force of that charge? Oops, did I not want to do that? I wanted to do that. All right, so if we just look at one of the charges here, we like to say that there's this electric field coming off of this charge. And so these are not vectors, these lines. These are just field lines. And this, in a way, helps us understand why the force falls off as 1 over r squared. So Coulomb said that the force between the charges is 1 over the distance squared between the charges. So the field lines go off, and just lines of electric field there. But the strength of it is really given by the density of these lines through a surface. So if you're near the charge, you could think of a little spherical balloon. And if there's 8 lines here coming through, the density would be 8 divided by this spherical surface area, which is 4 pi r squared. Now, as you go out and out and out from that charge, those 8 lines go to infinity. And so it's always the 8 lines divided by the surface area. And so then the density of lines is lower, and it's falling by r squared because the surface area is. And so that's how you can understand that you can draw the electric field as a vector. And if you drew it here, this distance away, and you drew the electric field vector here, it would have to be, if it's half the distance, it would have to be 4 times the length. But the electric field does point in the direction of these lines, and it points away from a positive charge and towards a negative charge. Okay, so now we can understand the force, because the force, if another charge happened to be there, would be QE. In the same here, the force is its own Q and the electric field of this charge. Right? So what we want is a plasma wave. What we want is charges pushing charges, okay? And so when I show like a large high point there, it's not that it's a wave that's up vertically. It's just the fact that underneath the maximum has the most number of negative charges, and then when it goes down, it's the most number of positive charges. And then it is a plasma wave, and so it'll get weaker and weaker and weaker, which means there's just less and less charges. And we actually don't care much about this. We care about this. We want these electrons. These are the ones that we're going to try to accelerate, and they're going to be pushed by this really densely packed bunch of other negative charges. Okay? And so it is the electric field that's going to do it. Again, I talked about this yesterday. So we're going to have a laser, and it's just going to go through at the 10 to the 18. It has to go through gas. When we get to the ones that we're going to try to do for the surgery, we're going to use almost solid density. We'll use a foam material or nano rod type material. But it's neutral until the laser pulse goes in. And so yesterday I talked a little bit about the fact that if you have intense enough light, you can have a multiphoton ionization. This is, I don't know Maria go, but Mary's picture there this time. That's funny. Anyway, that's what she told us when she was still a grad student. This happens around 10 to the 12 to 10 to the 13 watts per square centimeter. And I've said that even for the low one that we're going to try to do right by the tumor, we're going to go all the way to 10 to the 14. By 10 to the 14, the intensity is so high, and for those who weren't here yesterday, let me tell you, this, we don't, it starts out in some quantum level. This is like the Earth going around the sun in some level, but it's hard to think 3D. So we think again, because of height, that it's at some energy level, and to be able to escape, it has to get out of this well. So at the lower of the high intensities, between 10 to the 11 and 10 to the 13, the process is like this, okay? And that's like giving the energy to the electron so it can jump out of the well. But when the intensity gets even higher, and this is what I ended up doing for my PhD with my very intense laser, is that now the intensity, by 10 to the 14, the intensity of the light is so strong, it's actually warping the well that the electron is sitting in. And so it actually could warp it so much that the electron's just free to leave. And so that happens at about 10 to the 14, somewhere between 10 to 13 and 10 to the 14 watts per square centimeter. So since we need that intensity anyway to do the acceleration, we have no problem with charges being there because the material can't help but be ionized, and so we got charges everywhere. So we're making what's known as a plasma. All right, so back to how is a laser pulse like a deck? So yesterday's one, I talked about how to make a short pulse of light. And I talked about how you would need to add up all of these various colors of light to make this short pulse. Now, I just called it a wave of light. And then that sort of begs the question, what is a wave of light? So here's my wave of light again. What it really is if you start here on the axis, it's 0. The electric field, which I don't know, well, let's start with the first one right here. Here it's 0, the electric field is 0. As you go along, it goes up, gets higher and higher, and now it's a maximum. Then it goes back to 0, points the other way, and it comes back to 0 in one wavelength. From here to here, I guess it would be pointing up, 0, all the way down, 0, back up. That's 1. Okay, so that's here, down, and up. So it is an electric wave, but it is an electromagnetic wave. I haven't drawn the magnetic field. So if it is polarized such that the electric field just goes up and down in this plane, and you're traveling in that direction, and it's going up and down the electric field, the magnetic field is going in your direction. Okay, so when it's going up, the magnetic field is, and then when it's pointed down, it's doing this. Now, you may wonder then, why am I only drawing the electric field? And I've only talked about the electric field. Why is that? Well, that's because the electric force I showed you was QE. The magnetic force is Q times, we call B. I'm not actually sure why the magnetic field is B, but anyway, it is. It could be for bio, but don't know. I don't know a lot of history of physics, sorry. Anyway, but whatever, it's called B. And then it's also multiplied by the speed, okay? So the magnetic force is not about the charge, it's about the current or the moving charge, okay? And then if you look at the relative magnitudes of the electric force on a charge and the magnetic force on a charge, the relative magnitude is given by the speed of the charge divided by c, the speed of light. So as long as your charges aren't moving at the speed of light, nobody cares about the magnetic field, okay? So that's why a huge amount of optics never cares about the magnetic field, because usually the charges are not moving relativistic speeds. Now, I've already told you the goal here is to get it to be relativistic speeds. So by the end of the process, we do have to worry about it, but that's a detail that we're just not going to worry about today, okay? Because that's for the plasma physicist to deal about, but it's one of the many things that have to be thought of in order to make this thing work perfectly. But to get there, from going from the electron hardly moving to getting close to relativistic speed, we do not have to worry about the B, so we're not going to. All right, but it's there, and that's what our laser pulse is. So now back to the duck. Okay, so in both cases, the duck is making a wake behind it. Okay, so if the duck is swimming this way, I guess. If the duck is, because in the picture, oh no, the duck is going, that's good, because laser pulses only go left to right. Okay, good. So the duck is going this way, but, and making a wake behind it to help push the baby ducks this way. But if you look at the forces at play, the forces at play are vertical, right? The gravity is pushing down on the duck, or pulling down, I guess, on the duck, right? And then buoyancy is pushing back up. So then, and the electric field, let me just, before I explain it, the electric field, you'll see, is either up or down, going in this direction. And so if there's a charge there, we'll say it's a positive charge now because it's just easier, it would go up and then down and back up. And so the acceleration is all in this vertical, in the same way that the forces on the duck are vertical, but in both times, we're trying to push a wave behind and drag either the electrons or the baby ducks. And so what's happening? So now we have to know, what does it really mean? What is buoyancy? So when you push down on the table pushes back, okay? And that's, we just call that the normal force, okay? Because if nothing's moving and the V is 0, the forces have to go to 0. And so if gravity's pushing down, something else is pushing back up. But we have to actually look very small to see what's pushing up. Water, kind of easy to see, is that you'll see that the duck is slightly underwater. It's not that it's floating right on the very top. And so what's happening is the fact that the water is being pushed down with it, okay? And eventually what buoyancy is, the definition of buoyancy, is the fact that it pushes the same mass of water that's under the duck has out. And when that mass of water leaves, that's when they're balanced, okay? But the other way to think about it is the fact that the water is not a solid, and so the molecules are more loosely around each other, the pressure's less. But now the duck is pushing down on the water. And as the water gets pushed down, these water molecules look to the side and go, well, you guys aren't under pressure. Why are we under pressure? And poosh, out they go. You know, and there's always going to go from the high pressure to the low pressure. And so that's the pressure gradient is what's pushing the water this way. And so under the water that's been displaced to give her the buoyancy has gone out. It actually goes forward, sideways, and back, okay? And that's what's making the wave. And so then as the water gets pushed, it meets the other, and that's why the water wave is made. So now, how is the laser pulse doing it? Okay, so this is what you have to remember. Again, I said potential energy equals kinetic energy goes back to potential energy. All right, now I've drawn these little black dots, and these little black dots are to represent either a proton or an electron. But we'll go with proton in this case because it's positive and it moves in the direction of the electric field. The electron will just move in the opposite direction. All right, so now, this for now will be the laser pulse. And so again, here at the beginning of the pulse, the electric field is very small. And so what's happening here is that the electric field is going to push the charge, and then it's going to reverse its push and push the other way, and then it's going to push back. So what we have here is you could imagine a swing set, a bunch of swings, and people pushing small children on their swings. And maybe the person here is a small child and doesn't want to go fast, and so that mother is just gently pushing, okay? Now, there is a natural frequency to a swing, and so you want to push. You know, when you push a child on a swing, you wait till it comes back, then you push again, and you wait till it comes back, and you push again. And if your child doesn't want to swing very high, then you just gently push it. Right beside can be a bigger child that wants to go faster, so that person gets pushed more, but still at the same frequency. And finally, you have the child who has no fear at all, and so that one gets pushed and pushed and pushed. We're not going to push so high that it becomes nonlinear, because that's not part of the story. But that's the end, okay? And so they each start at if mothers can all be synchronized, they all start together, they all get up to their maximum, and they all come back to zero at the same time, they all go back to the minimum and back to the zero. And all in the same time. This guy goes up, down, back. This one goes all the way up here, all the way down and back, and this one goes all the way up here and all the way down and back in the same amount of time. So that means this electron or proton or child has to go a whole lot faster than this one, which means that this has the electron sitting here at the peak has a lot more kinetic energy than the ones on the edges, all right? And so now, instead of considering this the laser pulse, we can now consider that this is the kinetic energy hill. So this is the opposite of the way usually it gets explained to you about the ski hill and the potential energy. It's now a hill of kinetic energy, but that can turn into potential energy. For some reason, we call it ponderomotive in this case. I don't quite know why we changed the name, but what can I say? That's what it's called. So potential energy can turn into kinetic energy. And again, why do you pick up the speed as you go downhill? I said that the work being done to go up the hill with the C is the force integrated over the distance, okay? But if you start with the energy to go to the force, you do the opposite of integration, which is differentiation, also known as the gradient. And the change in this kinetic energy, or the potential energy, is along this direction, Z. And so that sets up this force, which is all the way around. Just like the duck displaces the water all the way around the duck, this laser pulse displays all of its charge, has a force on its charges all the way around. And I will tell you the force is equally on the positive and negative charges at one time where the positive and negative charges feel the same thing. Because while the electron is being driven down, the positive charge is being driven up. It's 1,000 times heavier, so it's not going as far. But the kinetic energy is still the same, right? It's not moving as fast, but it has 1,000 times more mass. And the electron's doing this, but it's got 1,000 times less mass. But the kinetic energy is the same. And the kinetic energy is turned into potential energy, and it's pushing. Now, I will tell you, I wasn't going to explain how proton acceleration works, because it takes, there's at least 3 types, but one of them is this. They just use thin films, the laser pulse comes in, it causes this potential energy, and it pushes out both charges. And, well, I'll just keep going on. The negative charges, though, travel faster than the positive charges. That sets up the next force, because these positive trailing charges go, wow, I'm so attracted to the negative charges, so that's the second one. And the third one, and this is why it's so much more complicated for protons, I used to if students, high school students, undergraduate students came into my lab, I would tune my pump lasers so I just felt it hit me. Because people don't realize this, but light does carry momentum. And so if you turn up a pulse and you let it hit you, you will feel being slapped by the laser. I did that until many, many students. And then I had a student that had darker skin, and it seemed to take the pigment away, and I went, I shouldn't even say this, I'm on camera. Anyway, I thought, oh my goodness, I don't know anything about that, so then I got scared, and so I don't let students get hit by the laser anymore. I've been hit many, many times, and it's never caused me any problem, but anyway, that scared me. But so that's the third way. So then the laser's going this way, and there's a momentum to push it. So those are at least 3 ways that the protons get accelerated. This is so this is the way, back to my story here. I should be careful. Anyway, there's a force going in all directions because of the Ponder motive energy. And that's how it works. So this is like the mother duck. The electric field is going up and down, but that's causing a force this way, and it's causing a force equally on the positive and negative charges. But you're going to, if you want to accelerate negative charges, you want to have this big one be the negative charges right here and let them go back and forth. It will set up a wave, right? As I already said, the electron charges will go further than the positive charges. They will then see each other and want to come back. And this is the same as the wave where the water hits it and back and forth and back and forth. We're just going to have charges going back and forth, but all traveling as this moves along in this direction. So that's really the whole story. And that's it. So now, how are we doing this? So, and why is it that Toshi contacted me? And, you know, how did Toshi go from a theorist to making sure his ideas happened? He became good friends with Gerard Moreau, who was my PhD supervisor. And so he wanted these 10 to the 18 watts per square centimeter pulses, and Gerard wanted to give them to him. So they've become friends. And so this is, obviously, my Nobel picture here. This is December 10th, 2018. We're celebrating. And this is, I'm just going to quickly tell you, you have a short pulse. You stretch it to make a long pulse so the density of photons stays low, because you don't want these multi-photon ionization effects happening inside here. Then you amplify, make it big, and when it's safely outside, and I'm going to show you a picture, now even air, you know, once the power gets really high, even air is a nonlinear medium, and you'd be ionizing the air. And so this is all done in a vacuum. I think the next, before I show you that. So then this is a picture of how the laser intensity has gone through the years. You will see the laser started in 1960. So going from just regular lights to lasers is the biggest change in intensity. These are ways to make the pulses short. This one I described yesterday. And then we couldn't amplify the short pulses because we would have nonlinear effects inside the laser rod. And so we had a laser hammer inside the laser rod, so we had to stop doing that. So that's why we needed to come up with this idea, and then it took off. And when Gerard used to show this picture, this used to be more a vertical picture, and he would show that by now we would be up here. I mentioned this as an answer to a question yesterday, if we get to 10 to the 29 watts per square centimeter, this is when we will blow up the vacuum and turn it into material. So that would be cool to see. I hope I'm alive when they get there. You will also see that it's rolling over now, okay? But these are the most, this is the most powerful laser in the world. It's 10 petawatts, and it's in Romania, but there's also one being built right now just outside of Prague. So they're both in Europe. The most intense laser is this one in Korea, but this laser is 10 petawatts. This laser is only 4 petawatts, but they have figured out how to make the spatial phases perfect so they could focus to single wavelength dimensions, okay? So these types of lasers, well, not so much that one, but these lasers here are the type of lasers that are being used at the above 10 to the 18 in order to see how far can we go. So just to show you what a picture looks like. So this, we're talking about trying to make something smaller than a hospital accelerator. So obviously this isn't necessarily it. This is just the compressor of that big laser. So this is the one that's in just outside Prague. Does it say what the town's name is? Well, it's just about 30 minutes outside Prague. And so this is the vacuum chamber where the gratings are inside. And this is the picture of the grating. So there's a human. And that tells you how big the gratings have to be to handle the energy and not get destroyed for the compressor. Okay, so these are really big lasers, and a lot of different experiments are done on these really big lasers, but I would say the consistent one that is done in almost all big lasers is particle acceleration. Okay, this is one of the big applications that we're really going for. But I don't work with those lasers because I'm not a team player, and I like, my favorite toy as a kid was Lego, so I like my lasers to be the size of Lego, small things. Okay, so then, probably around year 2000, or a little later, fiber lasers started to come along. And fiber lasers, they even had short fiber lasers that had 100 watts of average power. And solid-state lasers were usually stuck at the watt level, okay? And so I thought, well, why am I stuck with solid-state lasers? I should try to get into this fiber laser business. And the reason that the fiber lasers can handle so much more power than regular lasers is regular lasers usually have these solid crystals here. I mean, the petawatt lasers have crystals that are 1 meter in diameter, okay? I mean, they're not small. But it's a small crystal, usually, to start with. And the other problem is these crystals are pumped quite often in the visible, but lays in the infrared. And actually, the really big fusion lasers, the one that actually got to see scientific break-even of fusion, is actually pumped in the ultraviolet, and it lasers in the infrared. And so 90% of the energy pumped in has to go out as heat, not as light. And so this is the real problem. This is why they don't work very fast, because you have to get that heat out of the system so it doesn't crack and break. And so there's two problems. First of all, most of it's going out as heat, and also it's a small surface area to get the heat out. Now, a fiber laser, on the other hand, is pumped by diodes that are operating in the near infrared, and then the lasing light is just further into the near infrared. And so actually, the laser that I have in my lab is pumped at 975 nanometers, and it lasers 1030 to 1100. And so it's only about 10% of the energy has to go out as heat. The rest goes out in the light that you want it to go out in. And on top of that, the pumping goes up, back and forth. You can be 3 meters of fiber that's going up and down, up and down. And so you have quite a bit more surface area to radiate that much less heat. And so this is why, I've been to labs that have kilowatt fiber lasers, and I'm thinking, how scary is that? Because you wouldn't want to get your finger in that. Obviously, they have a lot of safety controls. Again, I don't like to work with anything that's unsafe. So, I'm willing to put laser goggles on, but I don't want to know that my finger could be cut off. So we stick with tens of watts. All right. So then the other thing was, we had to do CPA when we used solid lasers, because the nonlinear optics thing that happened took the beam and self-focused it down to a small thing, and that's when it became a hammer. But if you use fibers, the advantage is that it is guided. It stays a small beam, but it stays that small beam and is guided by the fiber all the time. So we don't have to worry about it self-focusing. And then there's an advantage. We can use the nonlinear optics to make more and more colors as it travels. So that's another big thing. If you think about my talk yesterday, the more color you have, the shorter the pulse. So just the summer before, the summer of 2018, I'm at a conference in Canada, and Frank Weiss comes, and he talks about his new fiber laser systems that can be both energetic and very short. And so then I had the chance to go and visit with him at the end of September 2018. And so just the week before I won for CPA, I asked him if he would make the lasers for me, and I got rid of all my CPA lasers, and I've gone to fiber lasers. So it's kind of a weird thing. But anyway, I stole this from his website, so it's not really very clear. But the point is, you can go in with this short pulse, and it makes more colors and more colors and more colors, and it disperses, 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 and becomes a longer pulse. But it has this nice linear chirp that a pair of gratings, the same as those giant gratings that is used for CPA, only now they can be smaller because the energy is microjoules instead of kilojoules, so it's 9 orders of magnitude less energy. They can be compressed. Now, this was the mistake I made when Toshi said, can you just make 10 to the 14 watts per square centimeter? I said, absolutely. He's got 1 microjoule. he's making 40 femtosecond pulses. Even if you call that 100 femtosecond pulses, you just have to focus down to 3 microns, and it's a 1 micron laser. Easy, easy, easy. And then I got off the phone and went, yeah, the gratings aren't actually at the end of the fiber. So that's a little bit of a problem. So then I phoned Philip Russell, who invented photonic crystal fibers. And so he's made hollow photonic crystal fibers, so you can put any gas you want in, or you can have vacuum in the hollow core. And you could maybe, in some cases, you can make this negative dispersion, right? So I called up Philip Russell, and I explained what Toshi and I were trying to do. And I said, do you think you could get maybe a 30-micron core, hollow core photonic crystal fiber that would have negative dispersion? He said, funny you should ask that, because I'm working with Wim Leemans on the very same idea. I went, well, because it's a good idea. Should we have more than one of us working on it? So I haven't heard that they've got it to work yet, but we're going to leave that part to them, because he is the expert in photonic crystal fibers. But my part is this right here. I didn't really explain how to get the electrons going at where they need to be. And I'm not going to explain it, but I'm going to tell you that Toshi told me. I also didn't really explain that in order for it to work really well, the pulse duration has to match one period of the plasma wave. And so that sort of limits. It's another reason why the pulses have to be short. But you can also do it by beat wave technology. And so he said, can you take your 1 micron laser and make it also a 2 micron laser? Well, actually, at first he said, can you make one with twice, we just need that factor of 2. So I thought I could double to green. And he said, you just need 10% efficiency. And again, I said, easy. Everybody can do 10% doubling efficiency. And then the student sent me his theoretical paper, and he means the longer one has to be 10%. And I'm going, that's a little bit harder. So that's the research project that I've got a brand new student working on just starting this fall, is that we are working on how to get our 1 micron to get 10% of the light into 2 microns. If you have the beat frequency, it's the beat frequency that has to match the wavelength or frequency of the plasma wave. So that all works, but for some reason, and I don't even 100% understand this, that also makes sure the beat wave puts the electrons exactly where they have to be to catch that wave. And so this is why he thinks this will work better. So I went, all right, I'm working on it. And so this is the final overall idea. Now this is not to scale, and I don't know who, this is something that Toshi sent me, but here it is. So this is the idea. We're going to have a short pulse somehow come right out of this fiber. We're going to need a lens. It can't be a traditional lens, because if we have a 30 micron going to 3 microns, it's still that means it's 100 times less intense. But that's still pretty intense. If you need 10 to the 14, 10 to the 12 is already very intense. And so normally we would use a reflective optics, but that's not going to work for this scenario. So I'm thinking now we're hopefully going to try to do a metal lens, right? It was a sort of a thin film lens using a nano description, and hopefully that will work. Then we go straight, so this is not to scale. So this part here, this is my 1 micron left of a tumor. This is only supposed to be 5 to 10 microns. Obviously, my fiber, if it's a 30 micron core inside, this will be about 250 microns. So this part does not match that part. But we're going to have a short pulse. We're going to have to find some kind of special lens. We're then going to hit nanomaterial, because again, the pulse has to go through at the same speed of the wave, and at the lower intensities, this can handle more electrons or more charges. So that's it. Now, of course, as soon as you hit it once, it would do a hole. So this is actually going to have to be some kind of moving tape. These are just a few things that have to be worked out. So don't look for this to be your radiation treatment anytime soon, but hopefully in the next decade or so, we'll have something like this. So that's the goal. That's what he's now amassed a large group of us to work together on it, and that's the story. Thank you very much.